So in this lecture we will be discussing about design of beams for flexure by using both methods, IS 456 2000 and SP16 methods. We will basically discussing design of doubly reinforced beams. First let me have the design data. So our design stipulations, beam size 200 by 500 mm, grade of concrete M25, grade of steel Fe 500, clear cover 25 mm, and our analysis moment from ETABS at ultimate load combinations. So MU, which will be 200 kilonewton meter. So you convert this value to Newton millimeter. So it will be 200 into 10 power 6 Newton millimeter. So this is our analysis moment. Analysis moment from ETABS. Clear. So I will be using longitudinal bars. Longitudinal bars, 16 mm dia, 16 mm dia, and stirrup diameter 8 mm. Okay, so here width of the beam, which is B, 200 millimeter. Total depth it is 500 millimeter. So whereas effective depth will be, so effective depth D equals overall depth 500 minus overall depth 500 minus clear cover, it is 25 plus 8 mm dia stirrup, diameter of longitudinal bars it is 16 divided by 2. So it is 500 minus 25 plus 8 plus 16 by 2, again it is 8. So 459. So effective depth will be 459 millimeter. So 459 millimeter is the effective depth. So let me calculate the capacity of the section. So MU limit equals so it will be 0.133 FCK BD square. So MU limit 0.133 FCK BD square. So this is for Fe 500 grade. So your MU limit will be So 0.133 FCK, it is 25, width of the section 200, and depth of the effective depth 459 square. So it will be 0.133 FCK 25, width 200, 459 square. So it will be 14,010,2865 Newton millimeter. So mu limit equals, so you divide this by 10 power 6, so then it will be 140 kilonewton meter. So this is your capacity of section. So limiting moment or capacity of section, which means your beam size is 200 by 500 millimeter. So this beam will have a capacity to resist a moment of 140 kilonewton meter, whereas your analysis moment mu, so it is 200 kilonewton meter. So this is your analysis moment. So if you compare these two values, capacity of the section and your analysis moment, so you can conclude, so your mu limit, which is less than mu, so mu limit is, I think it is 140 kilonewton meter, which is less than your analysis moment. So your analysis moment is 200 kilonewton meters. So in this case, you can say the given section is, the section is doubly reinforced section. The given section is doubly reinforced section. So in this case, the first step will be finding area of steel for mu limit, which means we will design our beam as, first we design our beam as balanced section. So area of steel, which is equal to, you know the formula, 0.5 FCK divided by Fy into 1 minus square root of, again 1 minus 4.6 multiplied by mu divided by FCK into B into D square multiplied by BD. So let me substitute the values. So 0.5 FCK, it is 25, Fy 500, 1 minus square root of 1 minus 4.6 into, so mu, will be 140 into 10 power 6. So here mu is mu is nothing but mu limit, because I will be designing my beam as balanced section. So divided by 25 into 200 into 459 square, 459 square into your width of the section 200, again effective depth 459. So 0.5 into 25 divided by 500 into 1 minus square root of, again 1 minus 4.6 into 140 into 10 power 6 divided by 25 into 200 into 459 square into 200 into 459. So it will be 864. So area of steel 864. So AST equals, so it is nearly equal to 865 mm square. So this is area of steel for balanced section. So I will call this as T1. So next, our second step will be reinforcement for balanced moment. Reinforcement for balanced moment. So what is the balanced moment? So your mu is 200 minus mu limit is 140. So your balanced moment will be 60 kilonewton meter. So mu is 200 kilonewton meter. Mu limit, so it will be 140 kilonewton meter. So balanced moment will be 200 minus 40, so it will be 60 kilonewton meter. So this is your balanced moment. To find the reinforcement for balanced moment, so you need to refer IS 456, IS 456 2000, that is class 38.1, page number 96, and it will be in annexure G. So let me open the code. So page number 96. Yeah, we are in the correct page number 96. Section with compression reinforcement. Section with compression reinforcement. So where the ultimate moment of resistance of section exceeds the limiting value mu limit, compression reinforcement may be obtained from the following equation. So in the second step, reinforcement for balanced section. So this is nothing but our ASC, compression reinforcement. So this is our compression reinforcement. So let me copy the formula. So formula is mu minus mu limit equals FSC into ASC into D minus D dash. So formula is mu minus mu limit equals FSC multiplied by ASC multiplied by D minus D dash. D minus D dash. So here you know the value of mu minus mu limit, and you know D dash and ASC. So FSC, here it is very important, FSC. So FSC equals, it is design stress in compression reinforcement corresponding to a strain of, so 0.0035 into XU max minus D dash divided by XU max. So for which first you need to calculate the strain. So strain epsilon SC equals, so what is the formula? 0.0035 multiplied by XU max minus D dash divided by XU max. So in this problem, your Fy value, it is 500 Newton per mm square. For 500 Newton per mm square, so you know the XU max, by D value. I think it is 0.46. Again, it is given in IS 456. I think this will be on page number 70. Sorry, page number 70. Yes. For 500 grade, XU max by D value, it is 0.46. So epsilon SC equals 0.0035 into XU max. So from this equation, XU max divided by, you know the D value. So D is effective depth. So it is 459 equals 0.46. So XU max equals 459 multiplied by 0.46. Multiplied by 0.46. So it will be 211. So it will be nearly equal to, so XU max, so 211 millimeters. So here XU max is 211 minus D dash. So you are calculating the compression reinforcement. Your D dash will be, so this distance from the concrete face to compression reinforcement centroid. So this will be clear cover 25 mm minus stirrup diameter 8 mm, and your reinforcement, it is 16 mm. So then D dash will be 25 plus 8 plus main reinforcement 16 by 2. So I think D dash, so it will be 25 plus 8 plus, so it is 41. So your D dash, it is 41 millimeter. So this is your D dash from this concrete face to, so this centroid of compression reinforcement. So this value it is D dash. How it is calculated? 25 clear cover plus 8 mm dia stirrup plus half of the longitudinal bar diameter. So D dash 41. So let me substitute in the below equation. So D dash 41 divided by, again XU max, it is 211. So strain epsilon SC equals 211 minus 41 divided by 211 multiplied by 0.0035. So it is 0.00281. So it is 0.00281. So this is your strain. This is your strain. So next you need to calculate stress. You need to calculate FSC, because you know the formula mu minus mu limit equals FSC multiplied by ASC into D minus D dash. So initially you calculated epsilon SC. Now it is required to calculate FSC. So your epsilon SC strain is 0.00281. Okay. Now you require to calculate FSC, that is stress. So for which either you can refer IS 456 2000 clause 38.1 page number 70. Yes, this is on page number 70. You have a stress strain curve for steel. So in x-axis you have strain, and in y-axis you have stress. So from this stress strain curve you can calculate the stress value for corresponding strain of 0.00281, or you can refer any textbook. So your grade of steel, it is 500 Newton per millimeter square here. So you have the strain epsilon SC and corresponding stress FSC values. If you refer any textbook, you will get the stress strain values. So this is for FE 500 grade. For strain 0, stress will be 0. When the strain is 0.00174, the corresponding stress will be 347.8. So when it is 0.00195, it is 369.6. When strain is 0.00226, 391.3. So 0.00277, In this case stress it is 413, 0.00312, so it is 423.9, so 0.00417, it is 434.8. so these values are available in any textbooks. So these values are stress corresponding strain. So here our strain value is 0.00281. It falls in this range. So our strain is 0.00281. So you can do linear interpolation. So here x1 is 0.00277, for which corresponding y1 will be 413. So x2 it is 0.00281, for which y2 it is required to calculate. For x3 0.00312, so y3 it is 423.9. you can do linear interpolation. And you can calculate the stress for this strain value. So what is the formula? So formula will be y2 equals x2 minus x1 multiplied by y3 minus y1 divided by x3 minus x1 plus y1. So let me substitute the values. So y2 equals, so x2 it is 0.00281 minus x1 0.00277 into y3 is 423.9 minus y1, so y1 it is 413 divided by x3 minus x1. So x3 0.00312 minus x1 0.00277 plus y1 it is 413. So let me solve this. So first it is 0.00281 minus 0.00277 into 423.9 minus 413 divided by 0.00312 minus 0.00277 plus 413. So it is 414.24. So y2 equals 414.25. it is the stress, unit will be Newton per mm square. So this is FSC for corresponding epsilon SC. Okay, so next Once you know the stress value, you have the formula mu minus mu limit equals FSC ASC into D minus D dash. So here mu minus mu limit, you know this value. So I think it will be 60 kilonewton meter balance moment. So it will be 60 into 10 power 6 Newton millimeter. So this value it is 60 into 10 power 6 equals FSC. I think it is 414.25. 414.25 multiplied by area of compression steel multiplied by D minus D dash. So D is effective depth 459 minus D dash value, it is 41. So let me simplify this. So it will be ASC equals 60 into 10 power 6 divided by 414.25 multiplied by, so this 459 minus 41. So let me solve this. 60 into 10 power 6 divided by 414.25 into 459 minus 41. So it will be 346. So your compression reinforcement ASC 346. So I will take it as 347 mm square. Okay. So this will be C2. So next, if you open the code IS456 on page number 96, again you need to calculate AST2. So you have the formula for AST2. So AST2 equals ASC multiplied by FSC divided by 0.87 Fy. So what is the formula? AST2 equals ASC multiplied by FSC divided by 0.87 Fy. So your AST2 it will be, so ASC 347 multiplied by FSC, I think it is 414.25 divided by 0.87 into Fy. Fy it is 500. So 347 multiplied by 414.25 divided by 0.87 multiplied by 500. So it will be 330. 330 mm square. So this is your AST2. Okay. So if you open the code, see here, the total area of tension reinforcement shall be obtained from the following equation. So that is AST equals AST1 plus AST2. So next it is to calculate AST. AST is total area of tension reinforcement. So this is your total area of tension reinforcement, which is equal to, what is the formula? AST1 plus AST2. So here AST equals AST1. What is the value of AST1? So initially you calculated area of steel for balanced section. So this will be your AST1. So this will be your AST1. I denoted it as T1. So 865 plus AST2 it is 330. So 330. So total area of tension reinforcement. So it will be 865 plus 330. So it will be 1195 mm square, or it is nearly equal to 1200 mm square. So this is your total tension reinforcement. And your compression reinforcement ASC, total compression reinforcement ASC, it is 347 mm square. So this is your tensile reinforcement, and this is your compression reinforcement. So how to detail? So here tension reinforcement. So first this will be T1. So T1 it is 865 mm square. Next it will be T2. So T2 it is 330 mm square. If you add these two, you will get total AST. So 865 plus 330, so it is nearly equal to 1200 mm square. So this is your tensile reinforcement. Whereas your compression reinforcement, so this is your compression reinforcement ASC. How much it is? So 347 mm square. 347 mm square. So this is the design of doubly reinforced beam. What is the procedure we have adopted? First, we design our beam for balanced section. Next, we will find the compression reinforcement for balanced movement. Compression reinforcement for balanced movement. In the next step, we calculate the AST2. This is your additional steel AST2. So once you add AST1 plus AST2, you will get total area of tension reinforcement. Okay, so this is your IS 456 method. So the same problem can be solved by using SP16 method. So now we shall discuss SP16 method. So for SP16 method, first you calculate mu divided by BD square value. So your mu is your analysis moment. So mu, it is 200 kilonewton meter. So this is your mu, analysis moment. So it will be 200 into 10 power 6 Newton millimeter. So 200 into 10 power 6 divided by your width of the section. It is 200. Effective depth, I think it is 459 square. So your mu divided by BD square value. So mu divided by BD square value. So 200 into 10 power 6 divided by 200 into 459 square. So it will be 4.74. 4.74. I will round off this value to 4.80. So your mu by BD square value, it is 4.80. So next you need D dash by D value. So your D dash, it is 41. Your D effective depth, it is 459. So it will be 41 divided by 459. So it will be 0.089. 0.089. So D dash by D. I will round off this value to higher value. So higher value is 0.10. These two I am referring. So mu by BD square value 4.80. D dash by D value 0.10. So now you can refer table 55 of SP16 on page number 91. So let me open SP16, page number 91. So page number 91. Yes, now I am in page number 91. So this table 55. So table 55, Flexure reinforcement percentage for doubly reinforced sections. So here you have grade of concrete 25, that is FCK 25, and grade of steel FE 500. So FY value 500. So your D dash by D value, it is 0.10. You have four values of D dash by D. First one is 0.05, next 0.10, 0.15, 0.20. In our problem, D dash by D value is 0.10. So 0.10. So mu by BD square value, it is 4.80. So for 4.80, note down the PT and PC. Note down the PT value and PC value. So percentage of tensile reinforcement and percentage of compression reinforcement. So PT, it is 1.321 and PC 0.409. So let me record it. So percentage of tensile reinforcement PT 1.321 percentage of compression reinforcement, it is 0.409. You convert this percentage steel to area of steel. So first let me calculate AST, that is tensile reinforcement. So PT BD divided by 100. So your PT 1.321 multiplied by 200 multiplied by effective depth 459 divided by 100. So 1.321 multiplied by 200 multiplied by 459 divided by 100. So it will be 1212. So it will be nearly equal to 1213 mm square. Next, ASC. So it will be PC BD divided by 100, which is equal to your PC 0.409 multiplied by 200 multiplied by 459 divided by 100, which is equal to 0.409 multiplied by 200 multiplied by 459 divided by 100. So it is 375. I round up to 376 mm square. So from SP16 method, you will directly get area of tensile reinforcement and area of compression reinforcement. So this is your tensile reinforcement. Tensile reinforcement, and this is your compression reinforcement. So this is your SP16 method. What is the answer you got in IS 456 method? AST it is 1200. So 1200 mm square. And ASC it is 347. So ASC it is 347 mm square. So there is a slight difference. Again, this is because of your mu by BD square value. So your actual mu by BD square, it is 4.74. I round up this mu by BD square value to 4.80. So that's why in SP16 method I am getting steel on the higher side. If you want the exact answer, then you can do linear interpolation and you can calculate the exact area of steel for 4.74.